Possible splitting in various geometries, we have studied it in detail. Now let us focus our attention on three geometries: octahedral, tetrahedral and square planar. If we consider any splitting, extent of splitting can be measured by one parameter, and that parameter is called as splitting parameter. If geometry of the complex is octahedral, we can say it is a octahedral splitting parameter. Accordingly, tetrahedral and square planar splitting parameters will be there. Question is, how to understand the extent of splitting, means how to measure the splitting parameter. Answer for this question is in absorption spectra. Let us revise. The splitting in octahedral field is in two parts. D orbitals splits in two sets. Lower set is T to G and higher set is EG. And the gap between lowest splitted orbital and highest splitted orbital, that's our definition of splitting parameter, and we say that splitting parameter as delta O. I'm not talking here about low spin or high spin complexes, whether delta O is larger than the P or less than the P. Here only the gap between the lowest splitted and the highest splitted orbital is important for us. If we consider the second geometry, tetrahedral, there splitting gap is reverse, means a gap between lowest orbital, that's a E, not EG, and highest splitted orbital T2 is nothing but the delta T, and you can recognize that delta T is smaller than delta O. Whatever the relationship we say, delta T is equal to 4 by 9 delta O, on what ground are we seeing? Are there any experimental proof? Yes, that only we are going to study. How to measure that splitting parameter, how to measure delta O and delta T. Now important point is square planar splitting. Splitting in square planar geometry. Here complications are there. In octahedral and tetrahedral, cases were straightforward. Now general point of view I am saying, I am coming to that point in detail later. But in square planar, already 4 levels are there. So what to consider? A gap between which orbitals will be the delta SP? As per our definition, lowest splitted orbital, that is a set of dxz and dyz, and highest split orbital, that's a dx square minus y square orbital, that gap will be the delta sp. But when electron excites, electron do not know whether it is the highest orbital or not. Electron will see which is the suitable orbital, upper orbital, there electron can proceed. Possibilities of excitation are there. Therefore, a perfect energetics for each orbital is important. What we consider highest splitted orbital dx square minus y square, its energy in relation to delta O. I am coming why we are saying it as delta O is 1.23 delta O, and next splitted orbital in square planar geometry is dxy orbital, and its energy is plus 0.23 delta O. See, the gap between those two is nothing but delta O. I can consider it is as delta 1. First splitting subparameter. Below dxy orbital, the orbital is dz square, but its energy is lower than that of the barycenter, and energy is minus 0.43 delta O. If I find the gap between second splitted orbital, that's a dxy, and this dz square orbital, how much will be there? This minus 0.43 plus 0.23. So summation is 0.66 delta O. It is a delta 2 subparameter gap I am considering. Now last energy level is a doublet of dxz and dyz orbitals, and its energy is minus 51 delta O. So how much gap is there between the dz square orbital and dxz and dyz orbitals? It is merely 0.08 delta O. So that is our third splitting subparameter in square planar complexes. I said it has what? Delta 3. Such many transitions are possible. Depending upon electronic configuration, we can guess which transition might have occurred. And in true sense, square planar complexes are rare, especially for D8 electronic configuration. These complexes are observed. In case of first transition series element, if ligand is stronger, then square planar complexes are there, and higher transition series elements, even if ligand is weaker because of the strength of the metal ion, the square planar complexes is observed, because in square planar complexes a lot of splitting is there, large splitting parameter is there. We are discussing their measurement in detail. What I want to say you now, let you consider octahedral, tetrahedral or square planar. Splitting between orbitals is there, and that can be measured by excitation of electron from one energy level to other energy level. To excite the electron from one energy level to other energy level, energy will be absorbed, and that will be revealed in one kind of spectra. Which spectra? Right, absorption spectra. By absorption spectra, we can understand which wavelength is absorbed or which wave number is absorbed. Wave number generally we express in terms of per centimeter, but for calculation purpose we should take SI unit, so we can express it in per meter also. So we can get wave number in per centimeter or per meter, and with the help of the data, with the help of the value of lambda, means wavelength absorbed or wave number related to the absorption, we can find out the energy for that wave which is absorbed. Energy of the wave which is absorbed is equivalent to energy needed to excite the electron from one level to other level. Are you following? Means that energy of photon is nothing but our energy gap. But this energy gap we will get for one transition, one photon. But general way, chemistry deals with per mole measurement. Means Avogadro's number of species, Avogadro's number of photons, Avogadro's number of transitions, Avogadro's number of electrons for which we deal with. Avogadro's number we consider as a standard one. So what we need to do, we need to express that energy in terms of joule per mole, or in order to have the sizable number, we express it in terms of kilojoule per mole. Now let us know how to do these calculations. See, by absorption spectra, we can get value of absorption. Means maybe it in terms of wavelength, or it may be in terms of wave, or it may be in terms of wave number. Here, wavelength is mentioned. Now, if we know the wavelength, then how can we find the energy? See the formula. E is equal to hc upon lambda. What is the value of H? Now in SI unit we should write all the values. 6.626 into 10 raised to minus 34 joules second. And what is the value of C? Speed of light, 3 into 10 raised to 8 meter per second. And then lambda from experimental basis, from absorption spectra we are getting, but majoritically we get lambda in terms of nanometer. So let it be angstrom unit, nanometer or picometer. We have to convert it to meter. How to convert nanometer into meter? That value into 10 raised to minus 9. That much meter. So meter should be there. So I represented the units there. Then you will understand meter and meter will get cancelled. Second and second will get cancelled. Will be left now only J, means joule. So energy for one transition, keep in mind, one transition for one photon we can find out by this expression. Similarly, if data provided is in terms of wave number, then how to find out energy? E is equal to hc nu bar. What is that nu bar? That's a wave number, and that in SI unit we should express in terms of per meter. But if it is expressed in terms of per centimeter, we have to convert it into per meter. Now see, in this H means Planck constant, 6 into 6 to 6 into 10 raised to minus 34 joule second. C means speed of the light, 3 into 10 raised to 8 meter per second. And this nu bar means wave number, we have to represent it in terms of per meter. If it is in terms of per centimeter, then we will multiply to that value by 10 raised to 2. We will get it in terms of per meter. Are these conversions clear? Again, we will get the value in terms of joule. Here you will find all units get cancelled. That is the reason why I represented units there, so that you will understand what may be the final unit of the answer. So final unit will be J, means joule. Now whatever the values of energy or that splitting parameter or the wavelength absorbed we found, those are in terms of joule. But I said conventionally we are expressing it in terms of kilojoule per mole. Then how to express that value in terms of kilojoule per mole? The value in joule into Avogadro's number, because we want to find out those many transitions from Avogadro's number of the electrons, Avogadro's number of the photons absorbed, Avogadro's number of the transition. So into Avogadro's number, what is Avogadro's number? 6.023 into 10 to 23 per mole. So that we will get the value in terms of joule per mole. But what is our intention? We want to find the value in terms of kilojoule per mole. And in order to find the value in terms of kilo, that's a term kilo, we are dividing it by means of the 1000. We will get answer in terms of kilojoule per mole. Then those values we can compare, correlate. It is a basis of finding of splitting parameter. Let it be the tetrahedral, octahedral or square planar. Calculations are different. So I am discussing it one by one. Yes, amongst all, the square planar complexes is a tough task to find the delta SP value, because many energy levels are there. Here we are doing approximation. Whatever I discuss in the octahedral, tetrahedral, it is at your level in order to understand the calculation of energy gap. In true sense, UV visible spectra calculations if we do, electronic spectra calculation if we do, then those are little different. That we will study at higher level, but at this moment, general chemistry point of view study we are doing. Keep it in mind. It is not exact study, but ideas will be clear to you. Main intention is that you should know the calculation of the energy levels by excitation of the electron, by absorption of the photon. It is the main intention. These are not wrong examples, but not so perfect calculations. In NiCN4 2 minus, Ni plus 2 metal ion is there, and this complex absorbs at wavelength 270 nanometer. I am considering where there is a maximum absorption. So wavelength is given. So if we know wavelength, can you find the splitting parameter? Splitting parameter we will see later, but at least we can find the energy for the photon. At least we can find energy for that transition. Now in Ni plus 2, which transition is possible? That let us see. See here, 4 energy levels are there. Highest is a dx square minus y square, then dxy, then dz square, and then dxz and dyz. In dxz and dyz 4 electrons are there, and in dz square 2 electrons are there. In dxy 2 electrons are there. Only in outermost orbital no electron is there. It is a d8 configuration. All electrons are paired. So actually many transitions are possible, but out of that, majoritically occurring transition or transition of low energy is none other than excitation of electron from dxy to dx square minus y square, and that gap is equal to delta O. In the previous videos I did a discussion about that energy levels. So that gap is nothing but delta O. And complete splitting parameter. What's the definition about splitting parameter? Energy gap between lowest split orbital and highest splitted orbital. And that gap is 1.74 delta O. From the wavelength of absorption, we can find energy of the photon absorbed. We can find energy needed to excite the electron from dxy set, dxy orbital to dx square minus y square. We can get delta value. Once we get delta value, we can get 1.74 delta value. That is nothing but delta SP. That's the splitting parameter for square planar complex. Let us start our calculation. A formula as usual, E is equal to hc upon lambda. H is equal to 6.626 into 10 to minus 34 joule second. C is equal to 3 into 10 to 8 meter per second. And wavelength absorbed. is 270 nanometer, means 270 into 10 raised to minus 9 meter. Perform the calculation, you will get answer as E is equal to 7.36 into 10 raised to minus 19 joule. It is in terms of joule. We want to express in terms of kilojoule per mole. How can I do that? Whatever the value in joule is there into Avogadro's number divided by 1000. Do the calculation, and what is the answer? That energy of photon absorbed to excite electron from dxy to dx square minus y square is 443 kilojoule per mole. Among these all complexes which we have studied, this 443 kilojoule per mole is the highest value. Therefore, square planar complexes shows the more splitting. But here, complete splitting of square planar complex we are not discussed. Complete splitting parameter for square planar we are not calculating. What is the complete splitting parameter? Complete splitting parameter is equal to this value of energy, which is equal to delta O into 1.74. So 1.74 into 443. What is the answer? 771 kilojoule per mole. See, highest value of the splitting parameter. Therefore, we say square planar complexes show the largest splitting. In order to know the span of the splitting, we are doing these calculations. The concept of calculation should be clear to you, so separate videos for different geometries are prepared here. Is the point of splitting parameter, means definition of splitting parameter, concept of splitting parameter, how to find the splitting parameter, how to determine the splitting parameter. Let it be the octahedral, means delta O, let it be tetrahedral, means delta T, and let it be square planar, means delta SP. It's clear to you? Again, in square planar, we are doing approximation 1.74 delta O. Variations may be possible, but concept should be clear. Therefore, I did this all discussions. Let us discuss in next part. Whatever the splitting parameter is there, it depends upon which factors. Factors affecting on splitting parameter. As a homework, one tricky question is there. Read the question carefully. I had given here absorption wavelength for square planar PTCl4 minus 2 complex. From that, you can find out delta 1, that's a sub-splitting parameter. We say it has delta O, usual calculation. But pay attention towards the next equation. Delta SP for this complex is equal to 1.33 delta O, high series number metal ion. Therefore, this relationship is changed. I repeat, delta SP is equal to 1.33 delta O, and I want value of delta SP in kilojoule per mole. Write only answer in the comment box. I am waiting for your answer.